Hello! In this video, we are going to prove the following lemma. For all natural numbers n and n plus the successor of n is equal to the successor of n plus n. Now, this lemma is based off of Tao's analysis, and the way that he defines addition of natural numbers is as follows. Right, so for any natural number m, we define 0 plus m to be n, and for all natural numbers n, we define the successor of n plus m to be the successor of n plus n. And we're also going to rely on another fact regarding natural numbers, which says that the successor of any natural number is also a natural number. Right, and this fact is given by axiom 2.2 in the book. Okay, so now let's get into proving the lemma. To start out the proof, let's give ourselves an arbitrary natural number n. And from here, our goal is to prove for all natural numbers n, we have that this is true. So we're going to proceed by induction on n. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 0. So really, we're trying to prove that 0 plus m plus plus is equal to 0 plus m plus plus. Now to start, since m is a natural number, we have by axiom 2.2 that the successor of n is also a natural number. And now, applying the definition of addition to natural numbers, if we take the m in our definition and substitute it for m plus plus, we have that 0 plus m plus plus is equal to m plus plus. But by definition of addition again, if we take the m in our definition to be the m in our proof, well, we have that 0 plus m is equal to m. So we can take this m right here and replace it with 0 plus m. So what we see here is that this is equal to this. So what does this mean? Well, we have proven precisely that this is true in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. Now the induction step, we give ourselves an arbitrary natural number n where this holds. So let n be a natural number and suppose that this holds. The whole goal of the induction step at this point is to prove that this is also true if instead of n, we replace it with the successor of n. So really, now we're trying to prove that n plus m plus plus is equal to n plus m plus plus. Okay, and to do that, let's start out by applying the definition of addition. If we take the m in our definition to be n plus plus, and we take the n right here to be the n in our proof, well, we have by part 2 that n plus m plus plus is equal to n plus m plus plus. Okay, and we know that the thing inside this parentheses is equal to this. So we're going to replace this with what we have here. And now applying the definition of addition again, if we take m to be the m in our proof, and we take n to be the n in our proof, we get that n plus m is equal to n plus m plus plus. So really, we could replace what we have in this parentheses with this. So what we see now is that this is equal to this. So what have we shown here? Well, we have shown that this is true, where instead of n, we have the successor of n. And that completes the induction step. So we've completed both the base case and the induction step, so this closes the induction. And since we've closed the induction, what that means is that we've proven that this is true for all natural numbers n. Since m was an arbitrary natural number, this means for all natural numbers n, we have for all natural numbers n, this is true. So we have proven precisely the lemma. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.